Okay, we have another example where we are going to use Lagrange multipliers for this function subject to this constraint. Okay, step one, we define this function capital F, oops, I always want to write a Z, lambda, by taking the function we're trying to maximize or minimize, and adding, remember this has to equal 0, which it does, lambda multiplied by this what we call G. Okay. And then we do all these partials. Again, if you see it, L1, L2, L3, it really means nothing. It's just the fact we need the partial with respect to x, partial with respect to y, and partial with respect to z, or lambda. But remember, this last one is just g. I'm going to cheat. And we set all three of those equal to 0. So partial lambda is the easy one because that derivative is 1, so we just get all that stuff. Okay. Partial with respect to x, we get negative 4x. X is a variable, y is a constant, negative 2y, 0, 1, 0, and then lambda, right? Because lambda times x, derivative with respect to x is lambda since lambda is constant. Set that equal to 0. Partial y, let's trade colors here. So 0 with respect to y, negative 2x. With respect to y, let's see, bring that 2 down. 2's would cancel, so we'd get negative 3y. 0, 2. And again, just a lambda, because we'd have lambda y, derivative of y is 1, so plus lambda. All right. Now again, we're trying to get x and y. Most common, solve for lambda, but there is more than one way to approach this. Like, I see if I multiplied this second equation by negative 2, right, I could cancel the x's. So whatever you see easiest, or we can multiply by negative 1 and add, and we could cancel these lambdas, right, if this were a minus here. But we'll go ahead and just solve for lambda. Well, if I solve for lambda in this case, I need to just subtract all this other stuff to the other side, so we get 4x plus 2y minus 1. Solving for lambda here, we get 2x minus 3y, plus 3y, right, switch the sign, negative 2, lambda equals lambda, right, these equal each other. So that means then that 4x plus 2y minus 1 equals 2x plus 3y minus 2. Solve for either of these variables. Let's see, if we go ahead and get x's on the left, y's on the right, I guess, subtract 2y. We'll go ahead and solve for y then, because that eliminated everything, right? So let's then add 2, and we'll subtract 2x. So negative 1 plus 2 is 1, and 2x, those y's gone, right? Y equals 2x plus 1. We need to take this now and substitute it back into L3. That way we have only one variable. So we're going to take L3 and we get x plus y, which is 2x plus 1, minus 5 halves equals 0. 3x plus 1, so 1 minus 5 halves is negative 3 halves. Add 3 halves, 3x equals 3 halves. Divide 3 or multiply by a third, and we get x is 1 half. All right, now if x is 1 half, we can get y, because right, 2x plus 1 is y, so 2 times 1 half plus 1. So we'd get 1 plus 1, y is 2. All right, again, depending what it wants. Most of these want to find the values of x and y to do this, right? To maximize that subject to that constraint. So we have it, our result is 1/2 and 2. 1/2 for x, 2 for y. If by chance they ask for lambda, that's fine. Just plug in your x and y into those lambda, one of the lambda equations, right? So lambda equals, we'll do this second one here, 2x plus 3y minus 2. So lambda equals 2 times 1/2 plus 3 times 2 minus 2. So it'd be 1 plus 6 minus 2 is 5. Now, it's meaningless, right, in this case. The original function didn't even have a lambda. However, that's how you wrap it up. If it does, in fact, want to know the Lagrange multiplier, the lambda that we used in order to maximize that function, subject to that constraint.